Hello, everybody. Welcome back to the Resenha Cosmica podcast. I'm here with Prajwal,
Hi again.
and we're going to be discussing inflation today with Dr. Luiz Filipe Guimarães, who is a postdoc here at UFAS. He completed his PhD in 2022, studying alternative ideas on early universe expansion. Those ideas being inflationary cosmology and bouncing cosmology. So we're delighted to have this discussion with Luis today. Hello, Luis. How are you doing?
Hi everyone. Thanks, Prajwal. Thanks, William, for the invitation. I'm doing fine. I hope you all are doing okay as well.
Yeah, excellent. So I think we'll start and keep it basic. So I wonder, Luis, could you just give us a brief overview on inflation and its role in modern cosmology?
So, as an introduction to this topic, I would mention that at first that it's the main area of research in primordial universe. So it's the most common solution for the hot Big Bang problems that arise from, like, people know this problem since the middle of the last century, and inflation is the most common solution to them all. So there are some alternatives, as we didn't have talked already, as I studied in my PhD. But inflation is a epoch right after the beginning of the universe, so it does not take into consideration how exactly the universe started, but it's like from the first 10 to the minus 36 seconds onwards. So we have this epoch of really fast accelerated expansion that lasted just a little bit. So it lasted just like 10 to the minus 30 seconds. So it was a really short amount of time, but the universe expanded really fast uh, in an exponential manner. And this period of inflation, of this period of accelerated expansion, happened because of a scalar field, or at least that's the simplest realization of inflation using a simple scalar field. And as I mentioned, that's the main area of research in regards to the primordial universe. The alternatives are, as I studied in my PhD, the bouncing cosmologies. There are also some other alternatives like epirotic cosmologies, or even eternal universes like pre-Big Bang cosmologies and so on, or even cyclic cosmologies as well, even though these are quite outdated nowadays. They're not really studied that much.
Okay, very good. So you pointed out that inflation was introduced to solve some issues we have in the hot Big Bang model. So can you maybe point out like what are these problems and how inflation is solving them?
Yeah, sure. So the problem is in the early 19th century, Alexander Friedmann solved the Einstein equations for the universe, right? For a homogeneous and isotropic universe, and this solution showed that the universe should be expanding, right? And as it is expanding, it means that in previous times the universe was smaller, right? So if it was smaller, it had a higher temperature, it had uh, the particles on it had higher velocities and so on. And when you extrapolate this solution to really earlier times, we get that the universe should be singular. So in t equals zero, so when the time is equal zero, so in the beginning of the universe, everything is singular. So the curvature of the universe is singular, the temperature and so on. That's actually the cosmological singularity problem, which the inflationary cosmology solution does not solve. So that's an issue that inflation actually does not take into consideration. The only problems that inflation tries to solve are regarding, for example, the horizon problem, which means that when we look at the CMB, so when we look at the cosmic microwave background radiation that spans across the entire sky, we see that, like, if we look for in different directions, for example, we see that, for example, in the north direction, the CMB has a temperature of like 2.75 Kelvin or close to it, right? And in the south, when we look to the south, the temperature of the CMB is exactly the same. Like, we don't need to consider the temperature fluctuations of the CMB for now, but the temperature is almost the same, right? In every direction that we see. But this north region of the CMB and the south region of the CMB, they were not in causal contact when we consider a Friedmann expansion of the universe. So if the universe expanded just like a Friedmann universe, these regions, like the northern hemisphere of the CMB, like the utmost north of the CMB and the utmost south of the CMB, they were not in causal contact anywhere, like in any time. So what exactly made these regions of the CMB have the same temperature? It's quite awkward because it's like having like dozens of thousands of people arriving at the same place with the same clothes, right? It's too much of a coincidence. These people had no way to interact, no way to match their clothes, but they arrived at a certain party with the same clothes. That's really strange. And that's kind of what happens with the cosmic microwave background. So we see that almost every direction that we see, not almost every direction that we see exactly, they all of these regions have the same temperature, around 2.75 Kelvin. So what made these regions have the same temperature? Because this, as I mentioned, a Friedmann expansion does not explain this. And there are approximately like 10 to the 6 regions of the CMB that should not have the same temperature. So it's like if we separate the sky in a million patches, all of these patches were not in causal contact in the beginning of the universe. They were never in causal contact until now. So they shouldn't have the same temperature. So that's the horizon problem. That's one of the biggest ones. The other one that we can mention is the flatness problem, which is connected to the curvature parameter of the universe. That is a quantity that is, of course, related to how much of curvature the universe has today. And it is a really small value nowadays. It's like smaller than 10 to the minus 2, 10 to the minus 3. But the issue is that if the universe is once again expanding only with a Friedmann expansion, so a phase of radiation domination followed by a region of matter domination, and then nowadays a dark energy expansion. If the universe follows this steps, these epochs, the curvature parameter shouldn't be that small because this parameter grows in time. So how can it be so small if it's growing in time? That's a kind of initial condition problem. So the curvature parameter of the early universe should be really, really, really small, such that nowadays it is still small, right? It grows with time, so it should have started really, really, really small. But that means that a small deviation of this value means that the universe today should be really different in terms of this curvature parameter, this curvature density parameter. So that's an initial condition problem. It's kind of this Friedmann expansion of the universe means that the universe should be really fine-tuned to achieve such small curvature today. So that's almost like to the degree of fine-tuning should be something really, really big, like 10 to the 20, 10 to the 30, It depends on how much earlier back in time you go to compare the curvature parameter then and the curvature parameter now. So it's really, really, really small. We shouldn't expect the universe to have such a high degree of fine-tuning in its initial conditions. And the third main problem of the Friedmann expansion of the universe is the so-called the primordial seeds problem. So it's basically how voids, how galaxies and clusters of galaxies form in the universe, because the Friedmann expansion, or as it was later called, a Big Bang expansion, it does not tell us how these fluctuations, how these density fluctuations that led to galaxies, how they led to voids. This expansion does not tell us how it happens. These perturbations should be inserted ad hoc. So we don't know when we're dealing with a Big Bang cosmology. So when we're dealing with a Friedmann universe, these fluctuations, they shouldn't exist. So they should have been put by hand. So it's once again kind of an initial conditions problem. So these are the three main problems of modern cosmology, of the Big Bang explanation for the early universe, which is just like this Friedmann expansion of the universe. These are the three main problems. So inflation tries to solve this.
So you mentioned about these very big problems which we are facing, which are like the fine tuning of the curvature, which is of orders like 30 or even 60 if you take a Planck scale as your initial value. So it's very fine tuned. And coming to horizon problem also, like the temperature of the CMB is so even that there is deviations in one part in 100,000. So the inflation should have some mechanism which it exactly solves this problem. So can you maybe explain a little on how inflation can solve these two big or three big problems you have mentioned?
Yeah, sure. So first, let me just remind us that this primordial seeds problem, these seeds are exactly the fluctuations that we see in the CMB as well. So when the CMB was discovered, it led us to believe that the Big Bang model, so the Friedmann universe model, was correct. But once the fluctuations in the CMB were found, that's when we realized once again that this problem of the primordial seeds was really important. But let's first go back to the horizon problem. So the horizon problem can be solved if these regions, all of these regions of the universe, if they were in causal contact before. Because if they were during some time, then there could be there could be thermal contact between all of these regions, so they were in thermal equilibrium, and that explains to us why the temperature nowadays, the temperature of the CMB is so close in all of these regions. So it's almost constant, right? So the solution that inflation gives us is that during a phase of accelerated expansion, the horizon, the particle horizon, so the region that defines causal contact between different regions, the horizon decreases. So it means that in the beginning, all of these regions of the universe could have been in causal contact. Then inflation happens, the causal contact shrinks, and then the Big Bang cosmology happens. So in the beginning of the Friedmann expansion, so in the beginning of the Big Bang expansion, all of these regions of the CMB really were outside the particle horizon of each other. So they were not in causal contact, but they were times before. So in the beginning of inflation, they were in causal contact. but then the horizon shrinks and then starts to grow again until the formation of the CMB. So inflation, a period of accelerated expansion, explains to us why regions that were in causal contact were then outside each other's horizons. So that's why they ceased to be causally connected with one another, and then followed the Friedmann expansion that we know. So that's the first method, like the first explanation for how inflation solves the horizon problem. So everything was in causal contact, so we can think of it as like a uniform patch of the universe, like a uniform patch that was really small. Then this uniform patch expanded exponentially, so they all of the regions of this uniform patch were expanded, so they got really far from each other. So that's another way to look at this decreasing of the horizon during inflation. And then they, after inflation ended, then the horizon started to shrink again. So these regions started to get into causal contact again, and finally around CMB scale, so around when the universe was like 350,000 years old, these regions started to be causally connected again, and then we see that their temperature is almost constant, like in the CMB. So a phase of accelerated expansion makes the horizon shrink. So these regions that were outside the horizon were actually into causal contact before inflation happened. So inflation helps us to define this initial condition for the Friedmann universe, right? So inflation helps us explain why these particles, why all of these regions were causally disconnected in the beginning of the Friedmann expansion. Then the flatness problem is quite simple to solve when we have an accelerated expansion. When we are in an accelerated expansion universe, this parameter, the curvature parameter, actually decreases with time. So it decreases with time with like the inverse of the scalar factor to the power of 2. So to the square of the scale factor. The scale factor is basically the size of the universe. If we know that this inflationary expansion is an exponential expansion, it means that the curvature parameter decreases exponentially as well. So in the beginning of time, before inflation happened, this parameter could have been really big, but during inflation, it decreases drastically, like 10 to the 60. It decreases really, really quite a lot. So it's really easy to make it small when the Big Bang cosmology starts to happen. So once the Friedmann expansion happens, this value of the curvature parameter was really, really, really small. So like 10 to the minus 20, 10 to the minus 60, or even like a really small value. And then it can grow towards order 10 to the minus 4, 10 to the minus 5, as are the values that are possible today, right? We have just an upper bound on it around 10 to the minus 3. So it's quite easy to solve the flatness problem during an inflationary expansion when we have an exponential expansion of the universe. That's quite simple. And for the primordial seeds, then we need a little bit more physics. So for these fluctuations to appear, we need some sort of material content to exist during inflation that leads to such perturbations. So it needs to lead to this cosmological perturbation. So there are fluctuations on the space-time metric of the universe, right? So we need another fluid to exist. So this material content, we expect it to be exactly the responsible for this inflationary regime to happen. And this happens precisely if we have a scalar field that has an equation of state parameter equals to -1. So it's kind of a cosmological constant. So this kind of scalar field has a scalar potential that is a lot larger than its kinetic energy. So if we have a scalar field in the early universe that has a large potential in regards to its kinetic energy, it will have an equation of state parameter approximately equals to -1, and that leads to an accelerated expansion of the universe. It leads to this almost exponential expansion of the universe. And to do so, we suppose that this scalar field exists in such a condition. So we call this field the inflaton. And the inflaton is this scalar field responsible for inflation. And as it is a scalar field in the beginning of inflation, it will have quantum fluctuations on it as well. So these quantum fluctuations of the inflaton field will cause some fluctuations in the background as well. So it will lead to cosmological perturbations. So the fluctuations of the inflaton field are responsible for the cosmological fluctuations in the universe. And these cosmological fluctuations that are tensor and scalar fluctuations, they lead to the fluctuations that we see in the CMB. So these cosmological perturbations, which are perturbations on the metric of the universe, they lead to these perturbations of the density of the universe. So they lead to fluctuations on the dark matter density, baryon density, photon density. And these fluctuations are responsible for the growing of structure in the universe. So dark matter starts to collapse into itself. So these perturbations grow. So this density fluctuation starts to grow and grow and grow. Baryons and photons are led to these growing fluctuations of dark matter, and then they lead to the structure that we see in the universe today. They lead to the formation of galaxies, they lead to the formation of clusters of galaxies, and so on. So basically, we solve the primordial seeds problem by explaining with physics how inflation could have taken place. So we need a scalar field. At least that's the simplest way to do it. We need a scalar field which has a large potential in regards to its kinetic energy. That's what we call a slow rolling universe, a slow rolling scalar field, sorry. So this slow rolling scalar field has a small kinetic energy, so it rolls really slowly along its potential, which is larger than the kinetic energy, right? So this slow rolling scalar field, the slow rolling inflaton explains how inflation can take place. And in doing so, it also explains how cosmological perturbations arise because exactly of the fluctuations in the field itself. So the quantum fluctuations of the inflaton lead to the cosmological fluctuations in the background metric of the universe, which of course lead to the formation of structure that we see today.
Okay, lovely. So it seems like instead of taking this Friedmann cosmology from the very beginning, that by inserting this inflationary period, that we are able to solve a lot of these problems that come with the Friedmann cosmology. And I suppose so to get a bit more into the details of this inflationary period that we have. You mentioned quite a few times there that scalar field. This inflaton field, which drives inflation, is a scalar field. What exactly is a scalar field?
So a scalar field has just one degree of freedom. So we have we can separate fields into the amount of degrees of freedom that they have. So we have scalar fields which have just one degree of freedom. We have vector fields. We have tensor fields. So a scalar field in particle physics are not that common actually. So we in the standard model of particle physics, we expect it to be at least the Higgs field as a scalar field, and the inflaton field should be another type of another kind of field. We don't know exactly from where it happens. So there are some string theory related arguments that lead to the inflaton to exist. Some people even think that the Higgs field can lead to inflation as well. So a scalar field is basically one type of field, just like the electromagnetic field or the gravitational field, but it just has one degree of freedom, just a scalar degree of freedom in its decomposition.
It's important that inflation should be a scalar field, because if it was like a vector field or something, then we would have expected kind of anisotropic expansion in the universe today, right?
Yes, exactly. And also different fields could lead to different kinds of cosmological perturbations. So, for example, we don't expect it to be any kind of vector perturbations in the universe. We expect it to be scalar perturbations. We expect there to be tensor fluctuations as well, which are the gravitational waves. But we don't expect like vector fluctuations to survive until today. But maybe if the universe had a vector inflationary field, it could lead to some of these problems as well. But that's not something that people had never tried to compute. So there are some models that try to use vector field as well. I'm not an expert in any of those, but they were tried in the beginning of the research on it. And yeah, we expect the inflaton field to be a scalar field. Exactly.
Okay, continuing on that, like you already explained some aspects of the dynamics of how this field should behave in the early epochs, like it should vary, the kinetic energy of this field should slowly vary compared to the potential. And all this should happen in the very, very early epochs. Like we are talking about inflation, like it should have happened somewhere when the universe was 10 to the power minus 36 seconds, and it should end after some time, like very quickly. It's like 10 to the power minus 32 seconds. Like it's very quick phenomena which happens in the very early epoch. So maybe can you give us more details on dynamics, like and how finally we get the matter particles out of inflation? Because in the early universe we had no matter particles, only the scalar field, and due to some dynamics, what we call as reheating or something, which should lead us to some matter particles. So can you maybe explain more on this?
And then some of those might be important for inflation as well. So we don't have a single field inflationary regime, but we have a multi-field inflationary regime. So there are some issues in inflation. People really need to take a look at it closely. It's a really nice field of research. There are lots of observational results that we can study as well. That's also an active field of research, because people have taken a look at the SIMB quite a lot. We had lots of observation of it from WMAP, Cope, and Planck. But we need to take a deeper look at cosmology as a whole to find clues about the primordial universe. So there are lots of alternatives, lots of different probes. We can start taking a closer look at the CMB spectral distortions. So we don't take a look at the temperature fluctuations of the CMB, but we take a look at the spectral deviations of it. So the black body deviations from it, like the mu and y distortions. We can take a look at some small scale predictions, like, for example, primordial black holes that are producing lots of multi-field inflationary models. And of course, they are produced in ultra slow roll regimes of inflation. We can take a look at this gravitational wave background radiation as well, the stochastic gravitational wave background, just like nanograv have detected. So that's also an active field of research in inflation, because, as I mentioned, slow roll inflation does not predict it. And I think that's the main point of it. Of course, non-Gaussianity as well. If we detect primordial non-Gaussianities at any scales, it means that single field slow roll inflation is not correct. So we can detect it on the CMB if we get better satellites in the near future. In the future, it may happen. We can try to detect non-Gaussianities using galaxy surveys, cluster surveys, taking a deeper look at large scale structure formation. That's really important, even though the constraints on non-Gaussianity there are quite difficult to set. And well, as I mentioned, primordial black holes and stochastic gravitational wave background. These are some other windows to try to check how inflation took place. These are some really interesting fields of research. And if anyone wants to email me to talk about inflation, feel free to do it. There are lots of different types of inflationary models that are really, really fun to deal with. And well, some of them have some problems, some of them do not. So inflation really is rich in phenomenology.
So thank you very much, Luis, for talking us to today. It's been absolutely fascinating, and hopefully we'll see you soon then to talk about bouncing cosmology.
Thank you very much for the invitation, William. Thank you, Prajwal. See you next time.
See you.
See you.
Bye-bye.
More on how inflation ends, right? How the reheating takes place, and if we can explain also some other mysteries of the universe, right? Because we don't know exactly how baryogenesis took place. We don't know exactly how leptogenesis took place. So there are lots of stuff that we don't really know how it happened. So why there is the baryon asymmetry in the universe? We don't know. It may be connected to reheating or the stages right after reheating, right? So primordial physics, primordial universe physics is a really still active area of research, and reheating especially is a really murky field. We don't know exactly what really happened there, and it's really highly recommendable that people start taking a closer look at it. But we expect reheating to explain why the inflaton decays into the standard model particles, and then that's it, right? The universe reheats, right? Because during this oscillation of the inflaton field, the energy of the inflaton field becomes thermal energy for the universe, right? That's why the Big Bang is really hot, right? That's why in the beginning of the Friedmann expansion, in the beginning of the Big Bang nucleosynthesis, we have a really high energy universe. That's when we have all of the standard model transitions, right? We have the electroweak phase transition and so on. The reheating is responsible for the heating of the universe, right? The universe started, inflation made it colder, but then reheating heats the universe again, just like its name explains to us, right? That's why we call it reheating. But we don't know exactly what happens during reheating, and I hope that I explained quite in a bit general detail what happens, but it really is a little bit of tricky. We don't know how it happens.
Lovely. And so one other approach to inflation is that we can modify the geometry of space-time rather than adding a scalar field. So how does this work in terms of obtaining inflation through this method?
So if we go to these routes of like using modified gravity to explain inflation, we are expecting GR not to be the precise description of gravity when we have high curvature or high energy in the universe, right? So if we do this, we then can like add some terms to the Einstein-Hilbert action. For example, using the Ricci squared term, which leads to the Starobinsky inflation model of the universe, of the universe, right? We can have some other models, just like people have thoroughly studied in F of R gravity, in F of T gravity, and so on. So if we start with a different kind of gravity for the early universe, so not GR, but a modification of GR, then the equations of motion lead to different types of expansion, right? And in particular, if we use the Ricci scalar squared, just like in Starobinsky model of inflation, it leads to an accelerated expansion of the universe. So it leads to what we call a quasi-de Sitter universe, right? A de Sitter universe is a universe which expands exponentially, but in inflation we deal with a quasi-de Sitter universe. So an almost exponentially expansion universe. So that's what the Starobinsky inflation predicts. That's just like R squared inflation. And there are some other possibilities as well, but R2 inflation is the main one because it actually is the best suited model to explain the Planck results. So the Planck satellite results indicate that the universe has primordial perturbations that have a tilt. So the scalar perturbations have a tilt. So they have a scale dependency, which is defined in the spectral index, which is close to 0.96. And the tensor to scalar ratio, so the ratio between the tensor perturbations and the amplitude of scalar perturbations is really small. It's like smaller than 10 to the minus 3, this ratio. So Starobinsky inflation really is right in the mark. Predicts almost nothing in terms of tensor perturbations to be produced. So it predicts small tensor perturbations, so almost none of primordial gravitational waves to be produced. And it also predicts the scalar perturbation tilt to be around 0.96. So it's the best suited model because we just need to tune one parameter, which is basically the mass, which is related to this R squared term in the action. So it's just a one parameter model. It's really easy to explain inflation, this type of model. It's really simple. It's just based on this principle that GR is not right at higher curvatures. So if the curvature is larger, then a term which is R squared, so which is the square of the Ricci curvature scalar, it dominates over the Einstein-Hilbert action, right? And so inflation takes place because of this second term in the gravity action. But there are also some variations of it. Some people have studied other F of R inflationary models, F of R and F of the Riemann tensor, and so on. There are lots of ways to achieve an accelerated expansion using modified gravity.
Okay, good. So maybe now can you, so we discussed a lot of things, like we discussed what are the problems by inflation, problems of the Big Bang cosmology and how inflation tries to solve it, and the dynamics of the inflation itself. And now can you tell us like what are the unique predictions the inflationary theory proposes? Like, can you maybe explain like what are the unique predictions we can make from inflation?
So there are some unique predictions that maybe are not so unique. That's why I was researching on bouncing cosmologies in my PhD and during my master as well. But we expect inflation to lead to scalar perturbations that are red tilted, which means that the scalar perturbations their amplitude decreases with wave number, so it decreases towards smaller scales, so towards uh, small wavelengths, and that's the first prediction because that's what the Planck satellite detects. So that's what we see in the CMB, right? That's the correlation function that we see in the for the fluctuations of the CMB. We know that it is red tilted. So inflation really does predict the red tilted spectrum. It's quite easy to do it. That's not a big issue. And also, inflation predicts that these fluctuations, at least when we deal with a single field, so when we only have the inflaton field, and when this inflaton field is behaving as a slow rolling field, we expect that the fluctuations, so the primordial perturbations, are Gaussian in nature. So and up until now, we have no detection of deviation of Gaussianity. So at least until now, single field slow roll inflation is really the most possible description for the universe. But if we detect non-Gaussianities in the near future, it will for sure rule out dozens of models of single field inflation. Almost everything, or practically everything, that is slow rolling single field inflationary cosmology will be wrong. So in single field slow roll inflation, we expect red tilted scalar perturbations, we expect Gaussian fluctuations, and we expect small tensor fluctuations as well. So a small tensor to scalar ratio, at least for most of the models that people study nowadays. Because in the early research on inflation, people used to prefer chaotic inflationary models, but these chaotic inflationary models that were first studied by Andrei Linde, these models, they predict large tensor fluctuations. But as we have no detection of tensor perturbations up until now, of these primordial tensor perturbations, then we don't expect these kinds of models to be correct. But there are still lots and lots and lots of models that predict the small tensor to scalar ratio. That's what this Stravinsky inflationary model predicts, and so many others. And these are some of the most known predictions of inflation. But there are some other ones that people might want to take a look that are not so really common. And one of those is the fact that the perturbations, not only they are red tilted, but they are in phase. So the fluctuations in the CMB can only appear if these cosmological perturbations are in phase. if they're not in phase, so if they're a little bit more random, which does not happen in inflation, so inflation really predicts fluctuations to be in phase, so they have the same phase for all the modes. If they are in phase, then fluctuations can grow to lead to the perturbations that we see in the CMB. But if we detect somehow a disconnect, if we detect something that is out of phase, it also leads to deviation of inflation, an inflationary evolution as well. But that's mainly that's highly unlikely nowadays, because we know from observations of the CMB that the fluctuations of inflation should really have been in phase with each other. So that's another prediction that people don't usually talk about, but that's really a prediction of inflation, and that should be the case for every other primordial universe that tries to explain the universe that it is today, right? So we have this prediction. So basically, the red tilt for the scalar perturbations, the Gaussian nature for the perturbation as well, a small tensor to scalar ratio, the perturbations to be in phase, and I think these are the main ones.
I think so. I think I would also like to add one more prediction which inflation makes, which is very interesting, especially this month, because we had the gravitational wave background detection from the pulsars. So I think inflation also predicts the polarization CMB, which are due to this tensor perturbations which you were talking about. Maybe can you maybe explain a little about these things?
Yeah, sure. So actually, the tensor perturbations that the nanograv collaboration detected, they could be primordial in nature, but they are not. They are, like, we don't know exactly for sure, but they're not the same as the tensor fluctuations that we expect to detect in the CMB. So when I mentioned that the fluctuations of the inflaton field lead to scalar and to tensor perturbations, these perturbations are expected to be really, really, really small. We have no detection of them up until now, and these fluctuations, because of the scattering of the photons in the early universe when the CMB is forming, they lead to B-mode polarization and E-mode polarization in the photons. And the B-mode polarization of the CMB is not possible when we have only scalar perturbations. So detection of the B-mode polarization in the smoking gun for inflation or for any other early universe model that predicts gravitational waves, right? Primordial gravitational waves. But the nanograv results are in a totally different scale. The nanograv results, they indicate either that these gravitational waves are due to in spiral of really large black holes, or they are they mean that some way, somehow, the universe led to these really small scales gravitational waves. But these gravitational waves are not they're not found in single field slow roll inflation. So if you want to find an inflationary model that predicts the tensor perturbations that the nanograv collaboration detected, so that those gravitational waves, you should take a look at some other different types of models. You cannot do it in single field slow roll inflation. You need to go to a multi-field inflation, because then in multi-field inflation, the phenomenology is a lot richer. So you can have an enhancement of the scalar perturbations for small scales, and this enhancement of scalar perturbations leads to secondary gravitational waves. The second order gravitational waves, they're related exactly to the scalar perturbations. They're only relevant if the scalar perturbations grow quite a lot. And as we know, the scalar perturbations are quite small for CMB scales. So something should happen something should happen after the relevant scales for the CMB leave the horizon during inflation, and then the scalar perturbations starts to grow, and this growth of the scalar perturbations lead to the growth of tensor perturbations as well. But that's outside the inflationary regime responsible for the fluctuations in the CMB. That happens after that. So during some time in inflation, especially if you go to multi-field inflation and some other models, something happened that led to these secondary gravitational waves. That's the main explanation for the nanograv results when you go to this interpretation of them. If you go to this primordial interpretation of them, you expect them to be generated by inflation, but a different type of inflationary model. You cannot do it in single field inflation. You should do it in another type of inflationary cosmology. A multi-field inflationary cosmology, a curvaton field inflation, and so on.
Yeah. So far we have talked all the good things about inflation. So you pointed out how inflation can be the initial condition for all the large scale structures what we see today for the cosmology. But I think there are some drawbacks for inflation as well, especially when it comes to when we ask questions like what are the initial conditions for the inflation itself, or of course there are many other problems. So would you like to uh, elaborate on what are the problems or challenges we are facing in the inflationary today?
Yes, sure. So one of the main problems, as I have already discussed, is that inflation does not really care about the really beginning of the universe, right? So the cosmological singularity is still not solved. That's still the problem. Some people think that the homogeneity of the universe is not really explained by inflation, so some people do not like the horizon problem explanation for inflation. So people do not really think that such smooth patches of the universe should expand as the inflationary regime predicts. So, but this kind of criticism is not really common, and but of course, the primordial singularity is still a problem. The reheating is still a problem. As I mentioned, people need to study a lot more of reheating to really know if it is really well established, if it is really if it really makes sense, if it does not alters the cosmological perturbations, if it does not lead to perturbations that are not seen in the universe today. So there are lots of stuff to do. There are some other problems that are related to some high energy physics. For example, in the string theory context, there is a so-called swampland conjecture. So if we deal with string theory and if we want inflation to take place in a slow roll manner, we see that these models, these single field inflationary models, are not in the landscape of string theory. They're actually located in the swampland. So that's a problem. So we cannot have a quasi de Sitter expansion of the universe with just a single scalar field, at least not in string theory. There are some other problems like the Transplanckian problem. Some people believe that the perturbations that appear in the CMB, some of them should have had initial conditions to be set when the universe was at Planck scale. So when the size of the universe was at Planck scale. So how can one do it without quantum gravity? Some people really think that it means that inflation is kind of wrong somehow, that we should really take into account high energy details, Planck scale details. So these are the Swampland conjecture and the Transplanckian problem. These are mainly problems that are related to string theory and to this high energy physics context. And when we talk about some problems in inflationary cosmology, we also are talking about the alternatives to inflation, right? So when I said that some people do not believe that the early universe does not really, early universe inflation does not predict a solution to the horizon problem. Some people believe that a true solution for it should be a bouncing cosmology, right? So a universe that starts really big and then it contracts, bounces, and get in this Friedmann expansion regime. Also, some people do not believe, some people believe that the singularity problem should be addressed and bouncing cosmologies address it as well, right? Because the universe starts really big and it contracts, but it bounces back before it becomes singular again. So some people really prefer bouncing cosmologies to inflationary cosmologies because of these two issues. And some other details are, as I said, related to particle physics, related to the standard model physics. That's why we need to study reheating a little bit more. And that's why there are lots of research on alternatives of inflation and on different types of inflation as well, right? Not only single field scalar, not only single field slower inflation, but also multi-field inflationary models and so on. Especially because, once again, when we talk about string theory, we expect the universe to be filled with lots of scalar fields, lots of different scalar fields. Of course, it depends on the string theory program that you're using, but lots of scalar fields are predicted to exist, and then some of those might be important for inflation as well. So we don't have a single field inflationary regime, but we have a multi-field inflationary regime. So there are some issues in inflation. People really need to take a look at it closely. It's a really nice field of research. There are lots of observational results that we can study as well. That's also an active field of research because people have taken a look at the CMB quite a lot. We have lots of observation of it from WMAP, COBE, and Planck. But we need to take a deeper look at cosmology as a whole to find clues about the primordial universe. So there are lots of alternatives, lots of different probes. We can start taking a closer look at the CMB spectral distortions. So we don't take a look at the temperature fluctuations of the CMB, but we take a look at the spectral deviations of it. So the black body deviations from it, like the mu and y distortions. We can take a look at some small scale predictions, like for example, primordial black holes that are producing lots of multi-field inflationary models. And of course, they are produced in ultra slow roll regimes of inflation. We can take a look at this gravitational wave background radiation as well, this stochastic gravitational wave background, just like nanograv have detected. So that's also an active field of research in inflation because, as I mentioned, slow roll inflation does not predict it. And I think that's the main point of it. Of course, non-Gaussianity as well. If we detect primordial non-Gaussianities at any scales, it means that single field Zoro inflation is not correct. So we can detect it on the SIMB if we get better satellites in the near future. In the future, it may happen. We can try to detect non-Gaussianities using galaxy surveys, cluster surveys, taking a deeper look at large scale structure formation. That's really important, even though the constraints of non-Gaussianity there are quite difficult to set. And well, as I mentioned, primordial black holes and stochastic gravitational wave background. These are some other windows to try to check how inflation took place. These are some really interesting fields of research. And if anyone wants to email me to talk about inflation, feel free to do it. There are lots of different types of inflationary models that are really, really fun to deal with. And well, some of them have some problems, some of them do not. So inflation really is rich in phenomenology.
So thank you very much, Luis, for talking us to today. It's been absolutely fascinating, and hopefully we'll see you soon then to talk about bouncing cosmology.
Thank you very much for the invitation. William, thank you, Prajwal. See you next time.
See you.
See you.
Bye-bye.